So this is the first problem that we're going to try together using one of those LOL conservation of energy bar charts. A dart gun vertically launches a 15-gram dart 40 centimeters high. Determine the minimum energy stored in the spring when the dart gun was loaded. So like the others, we're going to start this off by making our LOL diagrams laid out. So for my system on this one, I'm going to include in my system the dart gun and the spring in the dart gun, as well as the dart. And I'll also include, I guess, the ceiling, since you could say when the dart gun hits the ceiling, it could dissipate some energy. So dart gun, dart, and ceiling, those are all the things that I'm including in my system. Then I'm going to list the different types of energy I'm dealing with: kinetic, UG, US on both sides, and then ETH on the right side also. For my initial and final settings, I'll just put E for energy on both of these sides. Okay, so before the dart gun was launched, we must have had some energy in the form of the spring. We don't know how much, but we must have had some energy in the form of the spring. We'll call the elevation of the dart gun 0, so we don't have any UG. Gravitational potential energy is 0, and kinetic energy would be 0 before the dart gun is launched also. All right, assuming the dart gun just barely makes it to the ceiling and happened to just barely stick there, that's how we can find the minimum energy stored in the spring. So basically how much energy to get that dart up to the ceiling. Meaning afterwards, the only type of energy we're going to have is UG, gravitational potential energy. So I don't have lines on this paper here, but I'm trying my best to make that the same height as it started with. All right, now we know an equation for US. We also know an equation for UG. We're actually just trying to find the total energy stored in that spring to start with. So I can write out my conservation of energy equation now in the form of initial energy must be equal to the final energy, plus we may have done some work on the system beforehand, but in this particular question there's no work being involved here. All right, and then below that we're going to list specifically what our types of energy are. I'm going to have to scoop my arrow over just a little bit here, my equal sign. Beforehand I had US, and then my final conditions I've got UG. Then I can lay out US equals, and then for UG I'm going to use mass times 9.8 times delta Y, because that's the definition of gravitational potential energy. So for this one, US is the mass of the dart in kilograms, would be 0.015 times 9.81 meters per second squared, times the height, 40 centimeters high. It's not very high, so we'll say 0.40 meters. Then multiply those, and that's telling us how much energy must have been stored in that spring in order to get the dart up 40 centimeters. 0.05886 is what I got. With 2 sig figs, we'll call that 0.059 joules. Normally I would just write this on the next line down, but I'm out of space, so I'm coming back up to the top. All right, that's how much energy we started with as our US to start with, and it was just transformed into gravitational potential energy as the process took place. So that's how you use the LOL chart. We started off with a pretty simple example here just to get the basics down, but you get the idea of keeping up with all your types of energy, then using the equations for those types of energy and making sure they're equal before and after.